Okay, so let me now talk about FETK briefly. So it's basically our set of tools for dealing with problems that have this general structure. So it's basically just a set of independent, more or less independent libraries, although there's sort of a dependency, very much the way you guys build things at FEniCS. We have this low-level abstraction layer that provides a little bit more than an abstract ANSI C layer. It also provides things like sockets and sort of a simple MPI layer and so on. But basically it just abstracts out the platform so that the rest of this stuff is sort of, you can get access to not only ANSI C but also iNet sockets, MPI, and so on platforms like Windows and Linux and so on without knowing what platform you're on. All that's buried in this little thin layer here. And I should say malloc has actually been in the Debian tree for quite a while because there are a few other codes that actually depend on malloc. One is APVS, which is a very popular package built on FETK for doing electrostatics problems. So it's sitting in Ubuntu also. Okay, so now what are these things? Well, so let's say something about that. So this is the package I just mentioned. It's a very thin abstraction layer that just allows us to port our stuff around in a very simple way just by porting this little layer. This is just a collection of everybody else's numerical tools that we like to use, like BLAS, LAPACK, RPACK, SuperLU. UMFPACK is in there now. In fact, we tend to use that now. SG is another little tool that I developed with Randy Bank. It's the sort of common graphics tool that both PLTMG and FETK use now to do things. It's basically a trackball rotator written in OpenGL with a little Windows system layer around it to make it run on Mac, Windows, and Xboxes. Linux X Windows boxes. And it has some nice features. In particular, it has a very high quality PostScript renderer. So it grabs the polygon feedback buffer from OpenGL and then does sort of it solves a linear programming problem to figure out the painter's algorithm to paint all the polygons from back to front. So you get an exact polygon rendering in PostScript. So we always use this tool to generate images for our papers. Okay, and then the Gamer is a new thing that we developed with, this was postdoc Zhaoyan Yu, who was from Chandranjit Bajaj's group, came to work with me for a couple of years. He's now at University of Wisconsin, Milwaukee. I needed a good mesh generator to improve on what we had available for just setting up problems in FETK, so we wrote a standalone tool that we called Gamer. Gamer stands for Geometry Preserving Adaptive Mesher. And basically, it was designed initially for biomolecules, but we use it for everything else as well. And what it does is it can do things. It can take input from many different types of data, but in particular, it can read in a PDB file description of a biological structure, and then it generates surface triangulations of the biological structure using sort of level set or Gaussian type descriptions coming from the PDB file. Or it can actually take a surface that another tool like MSMS has built, and then it does sort of mesh improvement or surface improvement algorithms to produce a high quality surface triangulation. And then it builds a volume triangulation using standard tools like TETGen. So these are just some images just showing you what sort of high quality surface and volume meshing we can get out of PDB input files. And we also use it to generate very different things like black hole domains for doing very different kinds of problems. Okay, and then finally, well, some other images. These are just various biological molecules that we've done simulations with, and these are all in our papers that have appeared in the last year. And I'll point to those at the end of the talk. And then finally, the fun element part, and this is the part that I'm realizing that I should probably start leveraging a lot of the FEniCS parts, because this is our codes, my codes FETK are developed by a handful of people over many years. So it tends to be a code developed like PLTMG, sort of based on sort of one continuous research program with some postdocs and students kind of coming in and out of the group. But in any event, so what MC is, it's basically the fun element kernel, and it has some unusual features, although these are now, I can see that FEniCS is using a lot of these same ideas now, and probably has from the beginning. But basically, my interest was initially I wanted to be able to solve problems on surfaces, and so what I needed was some abstraction of the domain manifold to be completely topological and to have the geometry kind of separated out, and also done in such a way that I could deal with multiple coordinate systems in a very transparent way that wouldn't affect the rest of the setup for the software. And so this ended up being sort of the paradigm that was used for FEDK. And then also I wanted to be able to handle these tensor type problems. When you're working with a PDE problem on a surface, then your equations basically are tensorial, and I wanted to be able to handle some very complex tensorial type systems like the one I'm going to describe in a few minutes. And so this sort of tensor language interface to the way you describe problems in FEDK was developed from the very beginning also. And then finally, I like to prototype things in 2D where I can see things and then have things just work in 3D. So there was a key decision that was made early on is that all the code paths should be identical. So it just works with the D-simplex. Okay. And some of the basic data structures that are used, I don't know what's used in FEDK for representing geometry and topology, but what we use, what's in FEniCS, but what we use in FEDK is something we call the ring vertex data structure. And what it is that every vertex is a primitive and every simplex is a primitive. We don't store edges and faces as primary data structures. They're grown sort of dynamically and deleted dynamically depending on what we're doing. But then all of the topology is represented by rings of simplices around vertices. And the way you do this with arrayable type data structures, meaning that all the data structures have the same size so that you can make arrays of them and deal with them efficiently, is that basically every vertex has a pointer that points to the first in a ring of simplices around it. So that's a fixed size data structure for the vertex in addition to its coordinate information. And then every simplex maintains the next pointer to the next simplex associated with its vertex. So with every vertex, with every one of its vertices, it points to that vertex and then points to one other simplex which uses that vertex. And so if you want to get to the ring of all the simplices which use a vertex, you just trace this ring and then one of the guys that has a null pointer at the end. And so for example, if I want to get the edge neighbor in this two-dimensional triangulation, Jin Chao is one of my collaborators. Then what I do is I intersect these two simplex rings. And if this is three-dimensional and I want to get a face neighbor, then I intersect the three simplex rings. And in 3 dimensions, if I want to get all of the simplices which share an edge, again, I would intersect these two simplex rings. And these rings are all finite length, bounded length if I have shape regular meshes. So these are all order 1 operations. They're algorithms rather than storage, so there's a cost associated with them, but they're all order 1. So all of the information we need to do mesh refinement, assembly, and so on, these are all linear complexity type operations in this kind of data structure. The way we handle, I'll say something about the way we do mesh refinement in this kind of a data structure. When we refine an edge using bisection, we create the edge on the fly. The edge is basically a storage location for the midpoint for doing bisection. And then the simplex that's bisected is replaced by one of the children. There's a new child thrown at the end of the list of vertices, or the end of the list of simplices. A new vertex is added to the end of the list of vertices. And so you maintain array-like data structures. And then all the pointers are adjusted in order 1 time so that you maintain a conforming triangulation. You do have to do a conformity loop if you introduce a non-conforming edge in the mesh, but again, that's handled in a sort of iterative procedure that results in a conforming arrayable triangulation. Mesh deletion or mesh decimation, where we delete things, is more complicated, but we again have an algorithm which maintains array-like data structures. We only create faces if we have an element where we need face degrees of freedom. Edges are created only for refinement. Okay, so how do we do nonlinear approximation using this sort of setup in FETK? Well, we do sort of a standard solve, estimate, mark, refine type loop where we do a very particular type of marking strategy that will allow us to prove something about convergence. So that you can view these sorts of algorithms as having this general structure. You solve the nonlinear problem, and then using the discrete solution, you come up with some estimate for the error locally. And then based on that error estimate, you do some marking strategy where you mark some, say, 30%, the top 30% in the list of error, the guys that have to say the largest error in some decision framework. So say you mark the top 30% of the worst error violators. And in fact, that's part of, the marking strategy can be, in fact, very complex, and one of the areas that people have been working quite a bit the last few years is to come up with a very simple marking strategy where you can still prove convergence results. So the interesting thing is that people have been using these algorithms for probably 30 years in finite elements that go back to at least the early 80s. But in fact, only recently have people really looked at whether you could show these things converge, and it's not at all surprising because if you start out with solving a coarse problem and you miss some information somewhere, and your error estimate never sees that information initially, then and the error estimate doesn't tell you to refine to enrich the information where the missing piece of information is, then you're lost. You have no hope of ever recovering the exact solution of the problem. So what you have to do is design marking strategies which essentially asymptotically see everything and yet are still local.